Have you ever wondered how the universe manages to work so perfectly, almost as if everything is tuned with impossible precision? The tiniest changes in the laws of nature would erase stars, atoms, even the possibility of us being here at all. Tonight, here on Fall Asleep to Astronomy, we'll drift into that quiet mystery. We'll explore how the cosmos balances on a razor-thin edge between chaos and nothingness, and why its harmony feels so unlikely. No rush and no pressure, just gentle curiosity as you settle into the dark. For now, settle in, and when you're ready, we'll begin the journey together, unhurried and warm. Imagine, just for a moment, that you and I are standing at the very edge of the universe, wherever that edge might be. The darkness around us is not empty at all, but softly crowded with distant glows. In your hands is a quiet, impossible telescope, one that does not just magnify light, but seems to peer into the structure beneath it, into the way reality itself is arranged. You lift it to the sky, and slowly, patiently, star systems begin to come into focus. Each one is its own little story, a star or several stars, encircled by planets, moons, rings, belts of dust, and storms of ice. Some of them look wild and chaotic, others neat and tightly bound. It is like drifting through an endless gallery, each frame a different sketch of what a solar system can be. The lens pauses on one system that feels eerily familiar. There is a yellowish star, not too large, not too small. There are planets circling in calm, wide paths. For a heartbeat, there is a strange sense of recognition, as though your mind is whispering, "I know this place," a gentle cosmic déjà vu. But when you look closer, the familiarity begins to dissolve. One planet that should be small and rocky is swollen and gaseous instead. Another world sits too close to its star, glowing with heat, where you expected a cool, distant orbit. Moons gather in unexpected swarms around one planet and seem oddly absent around another. The choreography is almost right, but not quite. It is like hearing a song, with one note bent a little out of tune. You shift your gaze again, and the telescope reveals yet another system, and then another after that. With each new view, the feeling grows stronger. These planetary families are not arranged the way ours is. Orbits are tighter, planets are larger or smaller than you would expect, and some stars wear their worlds like bright necklaces, all crowded in close. The more you look, the more a quiet realization settles in. The pattern you carry in your head, the layout of the planets you learned as a child, might not be the standard template of the cosmos at all. In the vast sweep of the Milky Way, with its countless stars and possible planetary families, a gentle but startling thought begins to take shape. What if the odd one out is us? What if this solar system, the little neighborhood that holds Earth and its moon, and the familiar parade of planets, is not a typical example, but a kind of cosmic exception? Astronomers have long suspected that many stars would have planets. It seems natural, dust and gas collapsing together, forming a star in the center and worlds from what remains. For a long time, people imagined that most of those systems would look roughly like our own, a calm star. A set of planets in neat orbits, with small rocky worlds in close and large gas giants farther out. It felt reasonable to assume that nature would follow the same recipe over and over again. Yet, as recent research and careful mathematical models have stacked up, a different picture has begun to emerge. The more we actually look, the more it seems that our solar system really does stand apart. Its arrangement, its quiet balance, Its particular mix of worlds and distances and sizes may be far less common than we once assumed. What began as a simple curiosity has turned into a gentle, humbling surprise. This is not just a story about stars and planets. It is also a story about cosmic good fortune. Human beings have always looked up and wondered where exactly we fit in the grand design, if there even is a design at all. For most of our history, the answer we gave ourselves was simple and comforting. In the old geocentric picture, Earth sat at the center of everything. The heavens turned around us like crystal spheres. The sun, the moon, the wandering planets, and the background of fixed stars all revolved around our world, as though the universe itself were a kind of stage and Earth the main character. That view held on for a very long time. It fit with what people saw when they watched the sky with their own eyes. The sun rising and setting, the planets tracing their slow paths. It also fit with a deep, quiet human desire to believe that home must be at the center of things, that importance and centrality are the same. Then, during the Renaissance, a different idea took root. Nicolaus Copernicus asked a question that seems simple now, but was revolutionary then. What if it is not Earth that sits in the middle, but the sun? In his heliocentric model, our planet became just one world among several, circling a star rather than ruling the sky. The universe did not shrink, it expanded. We were no longer the hub of everything, but part of a wider dance. This shift was more than a technical correction. It quieted the old certainty that we must be central and invited a new kind of humility. Over the centuries that followed, astronomers refined this picture, mapping planets, tracing orbits, discovering more about the sun and the stars beyond it. The more they learned, the clearer it became that our place in the cosmos might be small, but small did not mean insignificant. It meant we belonged to something vast. In the 20th century, voices like Carl Sagan gave that humility a gentle, poetic form. He spoke of Earth as a pale blue dot, a tiny speck suspended in a sunbeam, floating in a dark, endless sea. In that image, our world is not the center, but it is precious. It is fragile and rare in its own way, not because the universe turns around it, but because life has taken root upon it. For a long time, many scientists believed that, although we were not at the center of the universe, our solar system was still pretty ordinary. This quiet belief, sometimes called the commonality hypothesis, suggested that the overall architecture of our planetary neighborhood was likely typical of many others. A central star, inner rocky planets, outer gas giants, and perhaps some icy debris farther out. It felt safe to assume that this pattern repeated again and again throughout the galaxy, especially since we did not yet have much evidence to say otherwise. That quiet confidence began to waver when a particular metal craft was sent to orbit the sun and listen for the softest of shadows. The Kepler Space Telescope, launched in the year 2009, was built with a single, clear purpose: to find planets around other stars, especially those that might resemble Earth in size or in the distance at which they circle their suns. Instead of scanning the entire sky, Kepler chose patience over hurry. It stared at one small patch of the Milky Way, watching more than 150,000 stars all at once. It looked for the tiniest dimming in their light, a brief, repeating wink that would mean a planet had just crossed in front of its star, blocking a small fraction of its glow. Each little dip in brightness was like a heartbeat on a monitor, a sign that a hidden world had just passed by. The data that flowed back from this silent observer were nothing short of transformative. What returned were not just hints of solitary planets, but patterns revealing full planetary systems, some with multiple worlds crowded close to their stars, others with giants sweeping along in blisteringly tight orbits, far closer than Mercury is to our Sunday. The familiar script we carried in our minds began to feel strangely narrow. Kepler's discoveries made it gently but firmly clear. Most of the planetary systems we were finding did not look like ours. Hot Jupiters, massive planets hugging their stars in scorching proximity. Compact systems where several planets, all roughly the size of Earth or a little larger, circled in tight formation, closer than Venus is to our Sunday worlds, with years that lasted only a few of our days. The layout we grew up with its quiet inner orbits and distant gas giants, began to seem more like an oddity than a norm. When astronomers sifted through Kepler's harvest, they noticed something humbling. Planetary systems that closely mimic our solar system appeared to make up only a tiny fraction of what was out there. The combination of factors we take for granted, the spacing, the sizes, the gentle circular orbits, does not seem to be the default setting of the cosmos. It is more like one particular melody among countless others, played rarely but beautifully. Even though the original Kepler mission ended in the year 2018, its legacy has continued to unfold. It opened the door for newer missions, such as the TESS spacecraft and the James Webb Space Telescope, each designed to deepen our understanding of distant worlds and the stars they orbit. They are the quiet heirs of a simple yet profound idea: to listen carefully to starlight and let it tell us where the planets are hiding and what kinds of systems the universe tends to build. Taken together, the message from these instruments is both simple and enchanting. The universe is not a place of repetition and uniformity. It is a grand, sprawling canvas of diversity, with star systems arranged in ways we once would have called strange. What we used to imagine as typical now looks like just one possibility among many. To understand this better, it helps to think not just about planets, but about the stars themselves and how they gather. A star system is not always a single star with planets. Often, it is a more intricate dance. Some of the most common arrangements in our galaxy are binary systems, where two stars are bound together by gravity. They circle a common center of mass, pulling on each other in a slow, steady waltz. Sometimes, planets may orbit one of the stars individually. Sometimes, they might circle both stars together, like children running around a pair of adults holding hands. Beyond binaries lie triple systems, where three stars share a gravitational relationship. These can form intricate patterns of motion, with one pair of stars circling each other while a third moves around them from farther out, or other, more delicate configurations. Their orbits are governed by the same laws that keep Earth around the Sun, but the resulting paths can be far more tangled and beautiful. A true choreography of light in the dark. And the cosmos does not stop there. There are systems with clusters of stars bound together, each star perhaps with its own retinue of planets, or perhaps alone. There are rogue planets, worlds that no longer orbit any star at all, set adrift by gravitational encounters, and left to wander the darkness between systems like lonely travelers. There are even arrangements in which stars themselves are flung away from their birthplaces, ejected by powerful gravitational interactions, sent speeding into the quiet reaches of space, carrying with them whatever planets manage to cling on through the upheaval. When we step back and look at this wild variety of star systems, a quiet question rises. What does all this diversity really mean for how we see our place in the universe? If you imagine all these systems as notes in a symphony, our own solar system is not the main melody that plays again and again. It is more like a rare harmony that appears only once in a while, surprising precisely because it does not quite match the common themes. Most of the star systems we know are not simple, single stars like our Sun, with planets circling at respectful distances. Instead, many are doubles or triples, where 2 or 3 suns move around each other, sometimes with planets weaving through this complex gravitational dance. Against that backdrop, our solar system, with one quiet yellow star and a spread of planets, moons, asteroids, and comets, stands out. Some studies suggest that single star systems with a rich family of planets, arranged as ours are, may make up only a small fraction of all the planetary systems in our galaxy. It is as if we live in a modest house, in a universe of bustling multi-star cities, and yet, every now and then, the cosmos offers something that feels strangely familiar. One of those curiosities is the star system known as 55 Cancri, located roughly 41 light-years away in the constellation of Cancer. When astronomers first studied it in detail, it tugged at a very human instinct to look for another version of home. On first impression, 55 Cancri seemed almost like a cosmic sibling to our own system. Its central star is a yellow dwarf, much like our Sun in temperature and character. Around it orbits a family of at least 5 known planets, a small crowd of worlds whose presence alone invites comparison. Among them is a planet larger than Earth, a so-called super-Earth, moving within a region around the star where temperatures might allow liquid water to exist on its surface. This planet, called 55 Cancri e, is estimated to be around 8 times as massive as Earth. The combination of a Sun-like star, multiple planets, and a potentially temperate orbit led many minds, quietly and inevitably, toward the possibility of habitability, maybe even life. But as always in astronomy, a closer look softens the initial resemblance. The orbits of the planets in 55 Cancri are more eccentric, more stretched out and elongated than the nearly circular paths in our solar system. Their spacing, their interactions, the way they move through their years, do not echo the calm regularity we are used to. And perhaps most importantly, this system seems to lack a giant planet like Jupiter, sitting in the outer regions and acting as a massive gravitational guardian, shaping the structure of our system and, in many models, helping to stabilize the inner planets over vast stretches of time. In other words, even a system that initially seems like our twin turns out, under careful observation, to be built on different rules. 55 Cancri is not a mirror of home, but a reminder that even lookalikes can have deep differences. Instead of diminishing the specialness of our solar system, it quietly highlights it. Our arrangement of worlds, the presence of gas giants at particular distances, the balance of masses and orbits, becomes even more striking when held up against such near misses. To move beyond intuition and impression, astronomers have turned to a gentler, more precise language, mathematics. Instead of simply saying, "This system feels similar," or "That one looks different," they have sought ways to measure those similarities and differences, to classify them in a way that helps reveal the underlying rules of planet formation. A recent study led by astrophysicist Lokesh Mishra and his colleagues offers such a framework. They propose a model-independent way to describe and compare the architectures of planetary systems, meaning they do not start by assuming a particular theory of how planets form, but instead focus on what the systems actually look like, the masses of the planets, their sizes, and where they sit in relation to their star and to each other. From this, they build a tool that can tell us how ordered or chaotic a given system's layout truly is. Mishra has spoken of the need for something like a standard model of planet formation, an organizing scheme that could help explain why different types of systems appear as they do. His team's framework is a step toward that goal. It allows scientists to quantify how similar the planets in a system are to one another, and how their properties change as you move outward from the star. This is not just a mathematical game. It helps uncover patterns, hints that there may be general laws guiding the birth and growth of planetary families. In their approach, planetary system architectures are broadly grouped into 4 categories: similar, mixed, anti-ordered, and ordered. You can picture these as 4 moods in which a star might arrange its worlds. In a similar system, the planets tend to have comparable masses or sizes, especially as you move from one orbit to the next. In mixed systems, there is no clear pattern. Big and small worlds are scattered in a seemingly irregular way. Anti-ordered systems show a kind of reversed logic, where more massive planets might sit closer to the star, while smaller ones lie farther out. Ordered systems, by contrast, follow a gentle, intuitive progression. Planet masses increase or decrease in a steady trend as you move outward. Jean Alibert, another key figure in this study, has explained that this classification can be built not only on mass, but also on other properties: radius, density, even the fraction of water a planet might contain. This means you can look at a system through different lenses, asking whether the sizes follow a pattern, whether densities do, or whether the amount of water or volatile materials changes in a meaningful way from inner to outer worlds. When they run simulations and compare them with observations, a picture begins to emerge. Systems with similar architectures, where planets resemble each other from one orbit to the next, appear to be the most natural outcome of planet formation in many scenarios. It is as if, in those systems, the planetary nursery produced worlds in batches, baking cookies from the same dough, with only small variations in size and shape. Their mass architecture seems to come directly from the structure of the disk of material that surrounded the young star, tying a planet's internal makeup tightly to the overall layout of the system. Anti-ordered systems, on the other hand, tend to show a different pattern. Many of these are predicted to be rich in so-called wet planets, worlds with significant amounts of water or other volatile substances. The heavier inner planets may have held on to or acquired large reservoirs of such materials, giving these systems a potentially high number of oceanic or water-bearing worlds, even if their arrangement feels inverted compared to our expectations. By contrast, systems with ordered mass architectures, in which planet masses follow a gentle trend that seems almost designed, are more likely to host dry planets, according to the study's results. That may sound disappointing at first, since dryness suggests fewer obvious candidates for oceans or life as we know it. But it also means that when we do find a system that is both ordered and produces a habitable, water-rich world, we are looking at something truly unusual, a refined and delicate combination of circumstances. Lokesh Mishra notes that in their analysis, similar planetary systems appear to be by far the most common, making up roughly 8 out of every 10 systems visible in the sky. This does not mean they all look identical, only that they share the broad pattern of planets that are more alike than not. Ordered architectures, the category into which our own solar system falls, seem to be the rarest outcome of all. The study does not explicitly take our solar system and place it firmly into a box, but it does suggest that the kind of ordered architecture we see here, with small rocky worlds and close, larger gas giants farther out, and a certain gradual logic to the way things are arranged, is a rare result. In their simulations, Ordered systems of this kind appear in only about 1.5% of the outcomes, roughly 15 out of every 1,000 model designs. That small percentage underlines how exceptional our planetary layout truly is. So we are led gently to another question. What special conditions give rise to a system like ours? Why did our star and its planets not settle into one of the more common patterns? The answers begin far from here, in the cold, dark depths of space where stars are born. Every star system begins its life inside a molecular cloud, a vast, chilly region of gas and dust. These clouds drift through galaxies like deep, quiet reservoirs of potential. Within them, denser pockets slowly gather, sometimes nudged by passing shock waves or the gravity of nearby stars. Over time, these pockets collapse under their own weight. As they fall inward, they spin faster, like an ice skater pulling in their arms, and flatten into a rotating disk. In the very center of this collapse, a protostar forms, a young, hot object that will eventually ignite and become a fully fledged star. Around it, in the disk, countless grains of dust and particles of ice begin to collide and stick together. At first, the clumps are tiny, but over time, they grow into pebbles, then boulders, then mountain-sized bodies. This slow gathering of material is called accretion, and it is here that the blueprint of a star system's architecture is drawn. The outcome depends on many things: the total mass of the disk, the way that mass is spread out, the amount of angular momentum it carries, the mixture of elements and molecules present, the temperature at different distances from the star, even the timing of when and where certain big clumps form. Slight changes in these initial conditions can lead to very different families of planets. A slightly more massive disk might produce more giant planets. A different distribution of solid material might concentrate large worlds closer in. Tiny variations can cascade forward, amplified over millions of years, until two systems born from similar clouds can end up looking nothing alike. Given this complex sensitivity to starting conditions, it becomes less surprising that our solar system might be rare. To get small rocky planets in the inner region, giant gas planets farther out, relatively circular orbits, and the particular spacing and masses we see today, the molecular cloud that birthed the Sun and its disk must have had a combination of properties that does not occur very often. The timing of Jupiter's formation, the amount of gas available when it grew, the way it migrated or did not migrate inward and outward, the interactions between forming planets and leftover debris, all of these likely played a part. In this sense, the creation of a star system is a little like drawing a number in a cosmic lottery, governed both by chance and by the unbending laws of physics. The laws tell you which outcomes are possible. Chance, through the delicate fluctuations in initial conditions, determines which particular path is taken. Most draws produce systems that fall into the more common categories: similar, mixed, perhaps anti-ordered. Only rarely do the numbers line up to yield an ordered architecture like ours. When we realize that the odds of building a system like this one are astronomically low, it does not have to make us feel fragile or afraid. Instead, it can wrap our existence in a quiet sense of wonder. On one small planet, circling one quiet star, in one rare arrangement of worlds, life has found a way to think about itself and to look back at the universe that made it possible. And that simple fact makes our existence all the more remarkable. The rarity of our solar system does more than make us feel special. It quietly reshapes how we think about life beyond Earth. If the way our planets are arranged is unusual, then the circumstances that allowed life to appear here might be unusual as well. Suddenly, the question of whether we are alone is not just about how big the universe is, but about how often that delicate pattern of conditions repeats. When people talk about habitability, they are really talking about a web of gentle balances. Earth sits at a distance from the sun, where liquid water can exist on its surface. Its atmosphere is thick enough to hold warmth, but not so thick that it smothers. Its magnetic field shields it from harsh radiation. Its orbit is nearly circular, keeping the seasons steady. Even the presence of a large moon and the steady pull of outer giant planets may have played quiet supporting roles. If the overall architecture of our solar system is rare, then this whole stack of subtle alignments may inherit that same rarity. And yet life on Earth has proved to be astonishingly resilient. It thrives in scalding hot vents on the ocean floor, in acidic lakes, in frozen deserts, and in the crushing pressures of the deep sea. Tiny organisms cling to existence in places where human bodies would fail in an instant. This resilience leads to a tender, hopeful question. If life can adapt to such extremes here, could it also flourish under the strange conditions on distant exoplanets, in systems very different from our own? Planets in tight, hot orbits, worlds with thick atmospheres of exotic gases, ocean planets with no land at all, frozen spheres warmed from within by tidal forces or internal heat. These are not science fiction sketches, but real possibilities revealed by our telescopes. Some of them would be hostile to human life, but perhaps not to all forms of life. Somewhere between the familiar and the extreme, there may be a wide range of worlds where chemistry can begin to stir, where simple organisms might arise and slowly write their stories into rock and ice and sea. The search for extraterrestrial intelligence, often shortened to SETI, adds another layer to this picture. Instead of just asking where simple life might exist, it asks where technological civilizations might appear and how we might notice them. Radios, lasers, engineered structures, subtle signatures in the way a planet reflects its star's light. These are some of the things scientists quietly listen for. If our type of planetary system, with its ordered architecture and long-term stability, is truly rare, then SETI may need to think carefully about where it is pointing its ears and eyes. Perhaps we should pay special attention to the few systems that show hints of a structure like ours. Or perhaps intelligent life can also emerge in environments we have not yet learned to recognize as promising. There is a chance that our expectations are shaped too tightly by our one example, us. It may be that we are listening for familiar songs, while the universe is whispering in other keys. In the background of all these efforts lies a quiet, haunting puzzle known as the Fermi paradox. It asks something simple. If the universe is so vast, and if there are so many stars and planets, then where is everybody? Why do we not see clear signs of other civilizations? No great engineering works spanning star systems. No unambiguous signals reaching our radio telescopes. The sky, for all its beauty, is silent in ways that feel strange when set against the numbers. The rarity of our solar system adds another thread to this paradox. If it takes a special arrangement of planets, a rare architecture, to support the kind of long, stable conditions needed for intelligent life to arise and build technology, then perhaps civilizations are simply far less common than raw star counts suggest. It may be that the universe is full of planets with some kind of life, but that very few worlds walk the narrow path that leads from chemistry to consciousness to radio waves and space telescopes. Intelligence might be not just unlikely, but layered atop a long chain of unlikely steps. After wandering through history, tracing mathematical patterns, and lingering over the strangeness of our situation, we arrive at a quiet, reflective place. Our solar system exists because chance and law worked together in a very particular way. Gravity, chemistry, and the initial swirl of a molecular cloud set the stage. But small fluctuations, subtle timings, and delicate interactions nudged the outcome toward this exact arrangement of worlds. It is a cosmic lottery where the ticket is written in dust and light, and the winning numbers are almost impossibly specific. And yet, here we are, on a small rocky planet. In the mild glow of a yellow star, there is a species capable of asking how it came to be, of looking back at the universe and wondering why it is so well suited to letting questions arise at all. Our bodies themselves are proof of our deep connection to the cosmos. The carbon in our cells, the iron in our blood, the calcium in our bones, the oxygen we breathe, all of these elements were forged in stars that lived and died long before the sun was born. Some of those stars ended their lives in gentle ways, shedding their outer layers into space. Others chose a louder farewell. They collapsed and exploded as supernovae, scattering heavy elements across the galaxy like seeds on the wind. Over time, those elements joined new clouds of gas and dust, which collapsed into new stars and planets. In that sense, the story of our rare solar system is also a story of these violent, brilliant deaths. Without them, there would be no solid ground beneath our feet, no oceans, no air, no living tissue to hold the questions that keep us awake at night. The search for life elsewhere continues, made more complicated by the rarity of systems like ours, but also more urgent and captivating. Each exoplanet discovered, each new spectrum examined, each faint signal studied is a step into unknown territory. We do not yet know how often the universe rolls the dice and lands on a configuration that can host thinking beings. But the mystery itself drives us to build better instruments, write better models, and listen more carefully. Our solar system may be an uncommon thread in the vast tapestry of the universe, but it is the thread we know from the inside. It is the vantage point from which we look outward, the starting line for journeys we have not yet taken. From here, we can trace the pathways of planets, follow the arcs of comets, and learn to read the stories written in starlight. Far above, beyond the comfort of our own sun, the cosmos is restless. Among the innumerable points of light that sprinkle the night, some stars are quietly burning through their fuel, some are just being born, and some are nearing the end of their lives. When the largest of these reach their final act, something astonishing happens. In an instant, measured on cosmic timescales, a single star can outshine an entire galaxy. These events are called supernovae. They are stellar catastrophes of unimaginable power, and yet they are also acts of creation. For as long as humans have watched the sky, these sudden flares of light have captured our imagination. Ancient peoples, with no telescopes and no equations, saw new stars burst into existence where the sky had once been dark. To them, these brilliant intruders were omens, messages, or the deeds of gods. In more recent times, astronomers have learned to see beyond the omen and into the physics. A supernova, in simple terms, is what happens when certain types of stars run out of nuclear fuel in their cores. For most of their lives, stars balance gravity with fusion. Gravity tries to pull all their mass inward, while fusion in the core pushes outward as light and heat. When the fuel in the core is exhausted, that balance can collapse. The core caves in under its own weight, and in some cases, the outer layers rebound in a titanic explosion. For a brief period, that explosion can shine with a brilliance that rivals the combined light of billions of ordinary stars in the host galaxy. The total energy released in a single supernova can be equivalent to what our sun will radiate over its entire lifespan, a stretch of time measured in roughly 10 billion years. When you picture that, imagine compressing the work of billions of tranquil years into a moment of flash, so bright that it can be seen across vast gulfs of space. These explosions do more than dazzle. They are among the primary forges of the universe. Elements heavier than iron, such as gold and platinum, are thought to be created in the extreme conditions found in supernovae and related violent events. The gold in a ring, the iron coursing through your blood, the calcium that gives strength to your skeleton, the nickel and copper in everyday objects, all of these were assembled in the hearts of ancient stars and released into space when those stars died dramatic deaths. Long before there was Earth, there were stars tearing themselves apart, so that one distant day, planets and living beings could be built from their ashes. Even without modern instruments, people noticed when the sky changed. Long before space probes and digital detectors, careful observers recorded the appearance of guest stars that flared into view where the heavens had previously been dark. One of the earliest known records comes from Chinese astronomers in the year 185 of the Common Era. They described a new star that appeared in the sky, bright enough to be seen even in daylight for several weeks, and slowly fading until it vanished about 8 months later. Today, with radio and X-ray telescopes, we can see the thin, expanding shell of gas left behind by that ancient event, a structure we now call the remnant of that long-ago supernova. Another famous example lit up the sky in the year 1054. Once again, observers in China and in the Arab world recorded a guest star that appeared suddenly about 4 times brighter than Venus. It was visible in daylight for roughly 23 days and could be seen at night for nearly 2 years before it faded from naked eye view. Centuries later, when telescopes had become powerful enough, astronomers pointed them at the patch of sky where the chronicles said the guest star had appeared. There, they found a tangled, glowing cloud of gas and filaments, the Crab Nebula, the lingering echo of that stellar death, still expanding into space, still shining with the energy of particles and fields unleashed in that explosion. The fragile cloud of gas and filaments left behind by that ancient explosion is what we now call the Crab Nebula, the ghost of a star that once flared so brightly that people on Earth wrote about it in their chronicles. For the civilizations that watched these sudden lights appear and fade, such events were more than curiosities. They quietly challenged a deep belief shared by many cultures. The idea that the heavens were perfect and unchanging, a serene clockwork that turned without surprise. When a new star burst into view, brighter than any ordinary point of light, it was as if the sky itself had spoken out of turn. Some saw these events as omens, signs of coming fortune or disaster, woven into systems of astrology and prophecy. The stars, in that way of thinking, did not simply shine. They commented, they warned, they blessed. Today, we still feel awe when a supernova appears, but we no longer read it as a message meant personally for us. Instead, we treat it as an opportunity, an opening in the universe's quiet surface through which we can glimpse the engines running underneath. By studying supernovae, We learn about the life cycles of stars, the creation and spread of the elements, and the long, intricate history of our galaxy. Even as our understanding grows more detailed and more technical, these explosions retain their power to move us. They are reminders that the cosmos is not a still picture, but an unfolding story shaped by birth, growth, and spectacular endings. In recent years, a familiar star in the constellation of Orion has captured attention around the world: Betelgeuse, the bright red shoulder of the hunter. Betelgeuse is a red supergiant, a swollen and aging star nearing the end of its life. Toward the end of the year 2019, its light began to fade in a startling way. Observers noticed that it dimmed far more than usual, leading some to wonder, quietly and excitedly, whether we might be witnessing the first hints of a nearby supernova in our own cosmic neighborhood. For a time, Betelgeuse looked unusually faint, changing the familiar outline of Orion. Then, gradually, its brightness returned. The most widely accepted explanation is simple and elegant. Betelgeuse likely expelled a large amount of material, forming a cloud of dust that drifted between us and the star. That dust did not change the star itself, but it blocked some of its light from our point of view, making it appear dimmer. As the dust dispersed and thinned, the star's apparent brightness came back to normal. This episode became a gentle reminder that even the stars we think we know are restless. They pulse, eject shells of gas, shift and change over time. The night sky may seem fixed from one human lifetime to the next, but on longer timescales, it is full of drama. Stars are born, they live out their luminous years, and they die in a variety of ways, some quiet and some almost unimaginably loud. Every star you see has a story that began long before its light touched your eyes. That story starts in a nebula, a vast cloud of gas and dust floating in the darkness. Within these cosmic nurseries, certain regions become denser than their surroundings. Gravity, always patient, pulls those regions tighter and tighter. As the gas collapses inward, it heats up, and a small, bright knot of material forms at the center, a protostar, the star in its earliest still-forming stage. Over millions of years, the protostar continues to draw mass from the surrounding cloud. As more material falls in, the pressure and temperature deep within its core increase. Eventually, the core grows so hot and dense that nuclear fusion can begin. Hydrogen nuclei start to fuse into helium, releasing enormous amounts of energy. At roughly 27 million degrees Fahrenheit, in the core about 15 million degrees Celsius, the protostar crosses a subtle threshold and becomes a main sequence star, stable and shining. Much like our Sunday, most of a star's life is spent in this main sequence phase. For billions of years, gravity pressing inward and fusion pushing outward remain in balance. The star quietly converts hydrogen into helium, bathing its surroundings in light and warmth. But no fuel supply lasts forever. When the hydrogen in the core is largely used up, the star's internal balance begins to change, and what happens next depends very strongly on how massive the star is. For a star with a mass similar to that of our Sun, the core contracts and heats up, while the outer layers swell and cool. The star becomes a red giant, its atmosphere puffed up to many times its original size. Eventually, the core can no longer support further fusion, and the outer layers drift away into space, forming a delicate shell of glowing gas called a planetary nebula. At the center, what remains is a white dwarf, a dense, hot ember about the size of Earth, slowly cooling over immense stretches of time. Not all stars, however, are destined for such a relatively gentle ending. Some are born with far greater mass, and their deaths are correspondingly more dramatic. These heavier stars can go supernova, and exactly how they do so depends on their mass, their composition, and sometimes on whether they share their life with a close companion star. Astronomers classify supernovae into types based partly on the kind of light they emit. One broad category is called Type 1. In the spectra of these explosions, their light spread out into a rainbow of wavelengths. There are no clear signs of hydrogen, the simplest and most common element. Within Type 1 supernovae, there are subtypes, including a particularly famous one called Type 1a. A Type 1, a supernova, typically occurs in a binary system where a white dwarf orbits closely with a companion star. Over time, the white dwarf can pull matter from its partner. As this stolen material piles up on the white dwarf surface, the star's mass creeps upward toward a critical limit. Once it gets close enough to that limit, the conditions become ripe for a runaway thermonuclear reaction. The white dwarf, which had been quietly glowing, suddenly ignites in a titanic explosion that tears it apart, leaving no star behind, only a rapidly expanding shell of hot gas and newly formed elements. Other members of the Type 1 family, known as Type 1b and Type 1c supernovae, are thought to arise from massive stars that have already lost their outer layers of hydrogen, and, in the case of Type 1c, much of their helium as well. These stars still undergo core collapse, but because their outer envelopes have been stripped away by strong stellar winds or by interactions with a companion, their spectra lack the familiar hydrogen signatures. Another broad category, Type 2 supernovae, are perhaps what many people imagine when they picture a classic stellar explosion. These arise from stars significantly more massive than the Sun, at least about 8 times the Sun's mass, and often more. Throughout their lives, such stars burn through their nuclear fuel at a furious pace, fusing heavier and heavier elements in their cores. All the while, gravity pulls inward and the energy from fusion pushes outward, maintaining a precarious truce. When the star finally exhausts its usable fuel, fusion in the core can no longer hold off gravity. In a tiny fraction of a second, the core collapses, shrinking dramatically and heating to staggering temperatures. The outer layers, suddenly unsupported, crash inward, rebound, and are hurled out into space in an immense explosion. For a short time, this dying star can outshine the entire galaxy in which it resides. What remains after such a cataclysm depends again on the star's original mass. If the core is not too massive, it can stabilize as a neutron star, an object so dense that a spoonful of its matter would outweigh a mountain. If the core is more massive still, gravity may compress it even further, past the point where light itself can escape, forming a black hole. In both cases, the original star is gone, but its legacy is scattered in every direction during its life, and especially in its death. The star has been manufacturing and distributing heavy elements. Fusion inside the star builds elements up to iron in its core, and the extreme conditions of the supernova explosion can create elements heavier than iron. The blast throws these enriched layers out into space, mixing them into the interstellar medium. In time, those materials will become part of new clouds, new stars, new planets, the building blocks of future worlds, and perhaps future beings who will wonder about their origins, are spread far and wide by a single star's final breath. The sheer energy involved in a supernova is almost beyond human intuition. The total amount released can be roughly equal to the energy our sun will emit over its entire lifetime of around 10 billion years, concentrated into a brief event. Yet most of that energy does not show up as light. Instead, it is carried away by neutrinos, ghostly particles with almost no mass and almost no tendency to interact with ordinary matter. During a core collapse supernova, an enormous flood of neutrinos is produced in a burst, lasting only a few seconds. These neutrinos stream outward at nearly the speed of light, escaping from the star and traveling across the universe. About 99% of the explosion's energy leaves in this invisible form. The remaining fraction appears as electromagnetic radiation, gamma rays, X-rays, ultraviolet light, visible light, and longer wavelength emissions. The visible light is what our eyes and optical telescopes can see, and it is dazzling. A single supernova can become so bright that it masks all the other stars in its host galaxy, acting as a beacon that can be observed from millions or even billions of light years away. Astronomers use these beacons not only to study the physics of the explosion itself, but also to measure cosmic distances and to trace the expansion of the universe. In that sense, a dying star can illuminate not just its own surroundings, but the large-scale structure and history of the cosmos. For all their beauty, supernovae are not entirely benign. If one were to occur close enough to Earth, the intense burst of radiation could have serious consequences for life here. One key concern is the effect on our planet's ozone layer, the fragile shield of gas in the upper atmosphere that absorbs much of the sun's harmful ultraviolet radiation. A strong blast of gamma rays from a nearby supernova or from a related event called a gamma ray burst could alter the chemistry of the upper atmosphere and destroy a significant fraction of that ozone shield. With the ozone weakened or thinned, more ultraviolet light would reach the surface. This could lead to higher rates of skin cancer in humans and other animals, and it could harm microscopic organisms at the base of the food chain, such as phytoplankton in the oceans. Since these organisms play a key role in photosynthesis and in the health of marine ecosystems, their decline could ripple outward, affecting many other forms of life. In addition to gamma rays, a supernova emits high-energy cosmic rays, charged particles, mostly protons and atomic nuclei, accelerated to tremendous speeds. When these particles reach Earth, they interact with atoms in the atmosphere and create showers of secondary particles. An increase in cosmic ray flux from a nearby supernova could enhance the radiation environment at the surface and in the atmosphere, possibly influencing cloud formation, atmospheric chemistry, and biological mutation rates. The exact effects are still the subject of ongoing research, but the possibility itself reminds us that we are not separate from cosmic events. We are immersed in them. Amid all of this light and radiation, there is yet another subtle signal to consider, one that does not travel as particles or ordinary waves of light. Certain supernovae, especially those involving asymmetric collapse or rapidly rotating cores, can also send out ripples in the fabric of space-time itself. These ripples are called gravitational waves. They spread outward from the source, stretching and squeezing space by tiny amounts as they pass, carrying information about some of the most violent and energetic processes in the universe. Long before anyone could build machines delicate enough to feel those ripples in space-time, a quiet mind had already seen them in equations. In the early decades of the 20th century, Albert Einstein worked out his general theory of relativity, a new way of understanding gravity, not as a force pulling at a distance, but as the bending and curving of space and time themselves. In the mathematics of that theory, he found something subtle and beautiful. If very massive objects moved and accelerated in the right ways, they would send tiny waves through the fabric of space-time, spreading outward like ripples on a dark, invisible pond. Einstein imagined, for example, two dense stars locked in an orbit around each other, neutron stars, or perhaps black holes, whirling together in a tight embrace. Their motion, twisting the geometry of space-time, would create disturbances that travel outward at the speed of light. Supernovae, with their sudden collapses and explosive asymmetries, are also natural candidates. When the core of a massive star caves in and the explosion is not perfectly symmetric, the imbalance can launch gravitational waves outward into the universe. By the time those waves arrive here, they are unimaginably faint. They stretch and squeeze space by amounts far, far smaller than the width of a proton. They pose no danger to Earth. They are too gentle for that. But they carry information, a kind of echo of the violence that created them. Listening to these ripples gives us a new way to study events that would otherwise be hidden deep inside the glare of light and the fog of matter. On Earth, scientists have built extraordinarily sensitive instruments to catch these whispers, long tunnels where lasers bounce between mirrors, watching for the tiniest changes in distance as a wave passes by. In recent years, these detectors have indeed picked up gravitational waves from merging black holes and neutron stars, confirming Einstein's prediction and opening an entirely new window onto the universe. Supernovae are thought to produce such waves as well, though detecting them is challenging. Still, the very possibility adds another layer of wonder to these stellar deaths. They are not only bursts of light and showers of particles, they are also gentle tremors in space-time itself. Fortunately, the odds of a supernova exploding close enough to Earth to cause serious harm are very small. Most of the stars capable of such explosions are comfortably distant, but even so, understanding these potential dangers is important. It reminds us that we are not separate from the wider cosmos. Events unfolding hundreds or thousands of light-years away can, under the right circumstances, leave fingerprints in the rocks beneath our feet and in the patterns of life on our planet. As we have seen, supernovae are powerful events, shaping galaxies and seeding space with heavy elements. Yet, there is another, more intimate question. Have they ever shaped the story of Earth itself? Scientists looking for answers have found intriguing clues buried in ancient seabeds and locked in Antarctic ice. One of those clues is a radioactive isotope called iron-60, a special form of iron that does not occur naturally in significant amounts on Earth today. It is not produced in ordinary geological processes, but it is forged in the furious furnaces of massive stars and in the chaos of their explosions. When researchers discovered traces of iron-60 in deep ocean sediments and in the layers of Antarctic ice, they realized they might be seeing the dust of long-ago supernovae that drifted through our solar system and settled on our world. These traces suggest that, at certain times in the past, one or more supernovae exploded relatively nearby on cosmic scales, close enough that some of their debris reached Earth. One notable candidate is often called the Pliocene supernova, thought to have erupted roughly 2.7 million years ago. Some scientists have proposed that this event might have nudged Earth's climate, perhaps contributing to cooling during an ice age period. The idea is not yet settled, and many details remain under discussion, but the possibility itself is stirring. A distant star's death, subtly altering the pattern of ice and warmth on a small blue planet far away. There is also a broader theory that nearby supernovae may be linked to mass extinctions in Earth's history. In this picture, a supernova occurring at the wrong distance and angle could flood the upper atmosphere with cosmic rays, high-energy particles that would damage the ozone layer over time. With the protective ozone thinned, more ultraviolet radiation from the sun would reach the surface, harming delicate organisms, especially those living in shallow ocean waters. The smallest, most exposed forms of life, plankton, algae, and other photosynthetic creatures could suffer first. From there, the disturbance could ripple through food webs, affecting larger species and possibly contributing to waves of extinction. These ideas are still being tested, weighed, and refined. Scientists compare models, search for patterns in fossil records, analyze isotopes in rocks, and try to separate the influence of supernovae from other forces like volcanic eruptions, asteroid impacts, and slow shifting of continents. Whether or not any particular extinction event can be firmly tied to a stellar explosion, the studies themselves highlight a deeper truth. Earth is not an isolated island. It is immersed in a dynamic, interconnected cosmos, shaped not only by its own internal geology and orbit, but also by the grand weather of the galaxy. When we look up at the night sky, we are gazing into the past. Light from distant stars and galaxies takes years, centuries, even millions of years to reach us. But in another sense, we are also looking toward the future. Stars that are quietly shining tonight will one day swell, dim, and die. Some of them will end their lives in supernovae, filling their neighborhoods with heavy elements and sending out bursts of neutrinos, light, cosmic rays, and gravitational waves. What might the future hold for supernovae in our own Milky Way? Astronomers estimate that, on average, a star in our galaxy explodes as a supernova roughly once every 50 years or so. That does not mean we see one that often with our own eyes. Many of these explosions occur behind thick curtains of gas and dust that obscure them from direct view, especially in the crowded regions of the galactic plane. The last time a supernova in the Milky Way was bright enough to be easily seen without telescopes was more than 400 years ago, when Johannes Kepler carefully observed a new star in the constellation of Ophiuchus. Since then, the sky to the unaided eye has seemed quiet, but astronomers know that supernovae are still happening, hidden behind the dust. They use instruments that can detect X-rays, radio waves, and other forms of light that slip through the veils more easily than visible light. These methods reveal remnants of relatively recent explosions, expanding clouds of gas that are still hot from the energy of their birth. Meanwhile, certain stars have become objects of special attention, watched closely as possible future supernova candidates. Betelgeuse in Orion is one of them, a red supergiant that will almost certainly end its life in a core collapse supernova someday. Another often mentioned is Eta Carinae, a massive, unstable star system in the constellation Carina, wrapped in a bright, chaotic nebula created by past outbursts. Both are far enough away that their eventual explosions are not expected to pose a danger to Earth, but close enough to promise a spectacular show for anyone watching the sky if they happen to occur while humans are still here to see them. A recent study has added fresh detail to our picture of Betelgeuse in particular. This star has long been known for its semi-regular changes in brightness. It gently brightens and dims over time in a way that is somewhat predictable, but not perfectly clockwork. In a star like Betelgeuse, these variations are thought to come from pulsations, rhythmic expansions and contractions of its outer layers, as well as from convection, the boiling, churning motion of hot gas rising and cooler gas sinking. By carefully analyzing long-term observations of its light, researchers have identified several distinct periods in Betelgeuse's brightness changes, roughly around 200 days, 420 days, 230 days, and 185 days. They interpret these as different pulsation modes of the star. The fundamental radial mode, where the entire outer envelope expands and contracts together, and higher overtones, where different layers move in more complex patterns. This pulsation analysis, which takes into account the interplay between pulsation and convection, suggests that Betelgeuse is in a late stage of its life, likely burning carbon in its core, a step that comes after hydrogen and helium have already been consumed in earlier phases. The same study revisits the dramatic Great Dimming that captured public attention from late 2019 to early 2020, when Betelgeuse's brightness dropped much more than usual. The researchers propose that during this period, the star's effective surface temperature decreased by about 100 Kelvin degrees, a small change in absolute terms, but enough to affect its light output noticeably. At the same time, Betelgeuse may have ejected a considerable amount of material, creating a dense cloud of dust that further dimmed its appearance from our vantage point. As that dust moved and spread out, the star's visible brightness slowly returned to its more familiar level. Taken together, these observations lead to an enticing possibility. Betelgeuse could indeed be relatively close, in astronomical terms, to its final transformation into a supernova. Its advanced stage of nuclear burning, high luminosity, and complex variability all point to a star nearing the end of its life. Some astronomers have also noted that its relatively high rotation rate for a red supergiant might hint at an unusual past, perhaps a merger with another star, which could have spun it up and altered its evolution. Still, predicting the exact moment of a star's death is a bit like trying to say exactly when a candle will flicker out based on the shape of its flame. Even if a star shows many signs that it is approaching its final act, the remaining lifetime could be thousands or even millions of years. On human timescales, that is an enormous stretch. On cosmic timescales, it is just another brief pause. So while Betelgeuse is a prime candidate to one day light up our sky with a supernova, we cannot say whether it will do so tomorrow, in 10,000 years, or long after our species has moved on. What we can say is that when such a star does finally explode, it will offer a grand spectacle and a wealth of scientific insight. Detectors will listen for the rush of neutrinos. Telescopes across the spectrum will watch the light curve rise and fall. Perhaps gravitational wave observatories will catch the faint trembling of space-time as the core collapses. From a safe distance, we will witness, in real time, the birth of a neutron star or black hole and the dispersal of freshly minted elements into the galaxy. The study of supernovae, then, is not only about endings. It is about beginnings woven into those endings. Each explosion saturates the cosmos with heavy elements necessary for new stars to shine, for new planets to solidify, and for the chemistry of life to unfold. In that sense, every atom in your body that is heavier than helium carries a memory of such an event. When we trace supernovae, we are tracing the origins of the material from which we are made, following the long loop by which the universe turns stellar death into the raw ingredients for new worlds, and possibly, one day, for new minds that will look up and wonder as we do now. As we drift onward through this imagined journey among the stars, it becomes harder not to feel a quiet reverence for how grand and mysterious the universe truly is. Supernovae, with all their brightness and violence, are like punctuation marks in the long sentences of stellar lives. They show us that stars are not eternal lanterns, but living things with beginnings, middles, and endings. They forge new elements, scatter them outward, and weave an invisible thread of connection between distant corners of the cosmos. We have wandered through their different types, the ways they can threaten nearby worlds, the traces they may have left in Earth's own history, and the possibilities that lie ahead. Each supernova, as destructive as it appears, is also an act of creation. It enriches space with the ingredients needed for new stars, fresh planets, and perhaps eventually, new forms of life. To study supernovae is to study not only how stars die, but how the universe recycles itself and makes room for what comes next. They also hold up a mirror to us. When we remember that the atoms in our bodies were once parts of ancient stars, the phrase "made of star stuff" stops being a poetic line and becomes a simple, astonishing fact. The more we learn about these cataclysms, the more we see that our own existence is tangled up with the births and deaths of suns. We are not separate from the vast, dynamic cosmos. We are one of its subtle expressions. In the early days of stargazing, we had only our eyes and a few pieces of ground glass to help us see farther. Now, our curiosity has grown tall enough to build instruments that can leave the Earth altogether. In the closing days of the year 2021, a new observatory quietly rose from the launch site near Kourou in French Guiana, the James Webb Space Telescope, often shortened to JWST. It traveled out to a special point in space called L2, a place in the Earth-Sun system where gravity and motion balance in such a way that a spacecraft can orbit in relative calm. From that vantage point, shielded from much of the sun's heat and glare, Webb can stare deep into the darkness and collect faint, ancient light. Its mirror, made of many hexagonal segments of gold-coated beryllium, unfolds like a delicate flower once in space, far larger than the mirror of the Hubble Space Telescope. Its instruments are tuned especially to infrared light, the gentle glow of warm objects and very distant galaxies, whose light has been stretched by the expansion of the universe. In its first year of work, Webb has already given astronomers a series of discoveries that feel almost like new senses opening. Clearer views of star formation, glimpses of planetary systems in the making, and intimate portraits of dying stars wrapped in their final veils of dust. Among its first celebrated images was a deep view of a galaxy cluster called SMACS 0723. This cluster lies roughly 4 billion light-years from Earth, which means the light we see now left those galaxies when life on our planet was still evolving in forms very different from us. Hubble had observed this region before, revealing the cluster as a crowded gathering of galaxies. Webb, with its sharper infrared vision, looked again and showed us even more. Hundreds of previously unseen, faint, small galaxies scattered across the frame like grains of distant embers. What makes this even more impressive is how quickly Webb can build such a view. That particular observation took only about 12 hours of exposure. For Hubble to gather a similar amount of detail would have required several weeks of staring at the same patch of sky. The difference is like opening a window wider. More light spills in, and with it, more stories. These images are not just beautiful. They allow astronomers to study very young galaxies, ones that existed when the universe was still in its early youth, before many of them merged and grew into larger spiral structures like our own Milky Way. In some of the data from SMACS 0723, a study led by Rohan Naidu of Harvard University suggests that some of the faint galaxies may have formed only about 300 million years after the Big Bang. On human timescales, that sounds ancient, but compared to the age of the cosmos, it is very close to the beginning. There is another quiet marvel at work in that image. The galaxy cluster itself is so massive that its gravity bends the path of light passing near it, a phenomenon predicted by general relativity and known as gravitational lensing. This bending can stretch and magnify the images of more distant galaxies behind the cluster, making them appear elongated or repeated in different positions. Astronomer Massimo Pasquale and others have studied these distorted shapes and concluded that the cluster's gravity is warping the background light, pulling it into arcs and smeared patterns. Even the cluster SMACS 0723 itself appears somewhat stretched, perhaps due to a collision with another cluster in the past, a slow-motion impact written into the shapes we now see. Another of Webb's early gifts was a fresh look at a curious object known as the Cartwheel Galaxy, about 500 million light-years away. Astronomers first discovered it in the 1940s, but only now, with Webb's sensitivity and resolution, do we see it in such intricate detail. The cartwheel looks almost like a wooden wagon wheel, viewed from above, a bright central hub, a clear ring around it, and faint spokes connecting them. Its unusual shape is thought to be the result of a high-speed collision between two galaxies more than 400 million years ago. Before that encounter, the cartwheel may have resembled a more ordinary spiral galaxy, perhaps not so different from the Milky Way. When a smaller galaxy plunged through its disk, it sent out ripples of compressed gas and dust, like a stone dropped into a still pond. Those ripples triggered waves of star formation, freezing into place as the ring and spokes we see today. Webb's observations show that the central region of the cartwheel contains a great deal of hot dust, glowing brightly in infrared light. The ring itself and the areas extending outward from the center are dotted with knots of intense luminosity regions where many young, massive stars are being born. As the collision's energy continues to push gas and dust outward, new stars ignite along the way. The galaxy is still changing, still responding to the event, and ongoing observations will allow astronomers to watch this transformation unfold in slow cosmic time, while also teaching us more about how galaxies grow and reshape themselves after violent encounters. In the middle of the year 2022, Webb turned its gaze closer to home, astronomically speaking, and captured the fading glow of a dying star in a structure known as the Southern Ring Nebula. This nebula lies about 2,000 light-years from Earth. Hubble had imaged it before, revealing a soft, round cloud of gas with a bright star at its center. For a long time, only one central star was clearly visible, and the details of what was happening there remained somewhat mysterious. The Southern Ring Nebula is the product of a star that was once roughly 3 times as massive as our Sun. Over thousands of years, it has been shedding its outer layers, blowing off gas and dust that now form the glowing shell around it. As it lost mass, the core of the star shrank and heated, eventually becoming a white dwarf, a dense, dim object no larger than Earth, but with a mass comparable to the original star's core. White dwarfs no longer shine through active fusion. They glow with the residual heat of their past lives, gradually cooling over eons. Because the white dwarf is small and not extremely luminous, it does not stand out in visible light. Earlier images suggested that the bright star we saw in the center of the nebula might be the main actor, with the nebula itself simply a cloud of previously ejected material. Astronomers suspected that much of the gas and dust had formed a disk around the fading star, glowing as it was heated from within. Such a disk can be easier to build if more than one star is involved, with gravitational interactions shaping the outflow. Webb's infrared vision changed the picture. It was able to pierce the dust and see into the heart of the nebula with much greater clarity. In the new images, astronomers clearly identified a second, fainter star, the white dwarf that is the true source of the nebula's material. The brighter companion nearby helps illuminate the surrounding gas, making the structures more obvious. Webb also revealed delicate, concentric arcs and lines along the edges of the nebula, like ripples frozen in place. Those patterns are unlikely to have been created by a single star acting alone. Arola De Marco, an astrophysicist at Macquarie University, has suggested that the shapes we see may be the result of interactions with multiple companion stars over time. As the dying star shed its outer layers, its companions could have stirred and sculpted the flow of material, carving rings, arcs, and clumps in the gas. Some of those companions might now be too faint to see with our current instruments, or they may have merged with the central star long ago, leaving their influence written only in the geometry of the nebula. What Webb has firmly confirmed is the presence of that second young star near the white dwarf, a partner in this complex celestial dance. Even though no additional companions are directly visible, their existence remains a plausible explanation for the intricate patterns. Further observations with Webb will help astronomers not only understand the relationships among these stars, but also analyze the chemical composition of the ejected material. In the soft glow of dying stars, Webb has shown us how endings scatter the seeds of new beginnings, but it has also turned its gaze toward the other side of the story, the birth of stars, just opening their eyes to the universe. One of the most tender sights Webb has captured is the young stellar object known as L1527, nestled in a dark molecular cloud about 460 light-years away. In Webb's images, this newborn star does not appear as a simple point of light. Instead, it is wrapped in an hourglass of glowing material, two opposite lobes of luminous gas and dust, stretching away from a thin, dark band. That dark band is a protoplanetary disk, a flat, rotating sheet of gas and dust surrounding the infant star. From our viewpoint, we see it almost edge-on, as a narrow line dividing the two bright clouds above and below. The scale of that disk is staggering. It is roughly comparable in size to the entire span of our solar system. Somewhere within it, tiny grains of dust are beginning to stick together, forming clumps that may one day grow into planets, moons, and smaller bodies. The colors in Webb's image tell their own quiet story. Where the dust is thick and dense, the clouds glow with a deep orange hue in infrared light. In regions where the material is thinner, the glow appears bluer, allowing us to sense where the nebula is more transparent and where it is more opaque. The shapes of the lobes are sculpted by outflows of gas from the young star, jets that carve cavities into the surrounding cloud and push material aside. Astronomers estimate that L1527 is only about 100,000 years old, a mere infant by stellar standards. That is far younger than a fully formed star like our Sun, which took on the order of 10 million years or more to settle into stable hydrogen fusion. L1527 is thought to be approaching the point where nuclear fusion will become its main source of energy, meaning it is only just beginning its long adulthood as a true star. Because this system is still in its earliest stages, it offers a precious glimpse backward in time. By watching L1527, scientists can imagine what our own solar system may have looked like when the Sun was young, still wrapped in a dusty cocoon and surrounded by a disk out of which the planets would eventually grow. If planets do form around this star, some of them may one day be counted among the exoplanets we study, and a few might even have conditions where life could take hold. For now, they are only possibilities, hidden in the haze, but Webb lets us watch the first steps on that path. Another region where Webb has turned its attention is in the Carina Nebula, a vast cloud of gas and dust where new stars are being born in great numbers. Within this nebula lies a region catalogued as NGC 3324, whose edge Webb has revealed in haunting detail. In the images, the boundary between cooler, denser gas and the hotter, more tenuous regions above it looks like a jagged mountain range or cliffs rising into a glowing sky. These cliffs are not rock at all, but hot, ionized gas and dust, sculpted by the radiation and stellar winds from massive young stars hidden just beyond the ridge. Within and behind this wall, Webb has uncovered hundreds of previously unseen newborn stars, tiny points of light that were invisible at shorter wavelengths because they were buried in dust. The telescope also detected thin jets of hydrogen streaming out from the top of the nebula, narrow beams of material launched by very young stars as they feed on the surrounding gas. Such jets are like signatures of active star formation. They mark a brief, intense phase in a star's early life, a time when it is still gathering mass from its environment while simultaneously pushing some of that material away in focused outflows. These episodes are short-lived by cosmic standards, lasting perhaps up to 10,000 years. To catch many of them in the act at once is rare and precious. Observations like these are a new step toward understanding how stars grow, how their formation influences nearby planets and disks, and how entire nebulae are reshaped by the energy of their luminous children. Webb has also revisited a more familiar site with fresh eyes, the region known as the Pillars of Creation, part of a nebula in the constellation of the Eagle, roughly 6,500 light-years away. These pillars are towering columns of gas and dust, each stretching 4 to 5 light-years in length, like dark fingers reaching upward against a bright background. Earlier images from Hubble made them famous, but Webb's infrared view peels back even more of the obscuring dust, revealing clusters of young stars embedded within the columns. In the second pillar in particular, the tip glows with a reddish hue that resembles slowly flowing lava. This color indicates that stars in that area are actively forming and emitting jets as they grow, heating and shaping the surrounding material. Based on their activity, these stars are estimated to be around 100,000 years old, similar in youth to L1527. They are still in the stage where they are clearing away the clouds that birthed them, carving out cavities and channels through which light can begin to escape. Interestingly, scientists also believe that there are more stars in Webb's images than we can easily see in the mid-infrared. Some of the stars in this region have likely just completed their early development, shedding the dense envelopes of dust that once concealed them. Without those dusty cocoons, they are less prominent at the wavelengths Webb is using in these particular observations, making them harder to pick out against the background. Even so, the information Webb provides is more than enough to study how stars emerge from their birth clouds, how they interact with their surroundings, and how such regions evolve over time. From cradles of star formation, Webb has turned as well to objects that stand in the twilight between stars and planets, brown dwarfs. One such object, designated Glass JWSTBD1, lies about 2,000 light-years away. Brown dwarfs are intriguing because they occupy a strange middle ground. They are more massive than planets, but not massive enough to sustain stable hydrogen fusion in their cores, which is the hallmark of true stars. Because of this, they never shine with the steady brilliance of a star. Instead, They glow dimly, cooling and fading over time. Like planets, brown dwarfs have atmospheres and can host complex weather patterns. Some are thought to contain water molecules, clouds, and a variety of other chemical species. Studying them helps astronomers understand where the line truly lies between large planets and small stars, and how objects on both sides of that boundary are formed. For glass, JWS TBD1, Webb's initial observations suggest that it is roughly 30 times more massive than Jupiter, with a temperature around 720 degrees Fahrenheit. That is far hotter than any planet in our solar system, but cool compared to many stars. Because it is distant and faint, there is still much we do not know about it. Teams led by researchers such as Mario Nonino have emphasized that more observations will be needed to pin down its chemical composition, atmospheric structure, and other properties. Each new piece of data will refine our understanding of how such underweight stars come into being and how they evolve. Webb has also peered at another brown dwarf companion, one already known from earlier surveys, VHS 1256-1257b, a mouthful of a name for an object that nonetheless tells a clear story. This brown dwarf is relatively nearby, about 72 light-years from Earth, close enough that Webb can examine its atmosphere in impressive detail. In its light, scientists have detected signatures of water vapor and carbon dioxide, along with evidence of clouds made of tiny silicate particles, essentially grains of sand suspended high in the atmosphere. These observations reveal that brown dwarfs and giant exoplanets can have rich, dynamic skies, with clouds forming, dispersing, and perhaps raining particles downward in ways that we are only beginning to understand. By comparing brown dwarfs like VHS 1256-1257b with planets that orbit stars, astronomers can slowly piece together how atmospheric chemistry and weather depend on mass, temperature, and environment. Among the exoplanets Webb has studied directly, one of the first to be imaged is the gas giant known as HIP 65426b. This young planet, located about 385 light-years away, was initially discovered in the year 2017 by a ground-based telescope. Even after its discovery, studying it in detail proved difficult. In the infrared, the glare from its host star, HIP 65426, overwhelmed the faint glow of the planet itself. The star is roughly 10,000 times brighter than the planet at certain wavelengths, making the task akin to spotting a firefly next to a searchlight. Webb's instruments, equipped with special masks and techniques designed to block out starlight, managed to capture the first direct image of HIP 65426b, taken during its mission. The planet orbits far from its star, about 100 times farther away than Earth is from the Sun, which helped Webb separate the two sources of light. Even though the planet remains just a small dot in the image, this direct view is valuable. It allows scientists to analyze its light and gather clues about its temperature, possible atmospheric composition, and formation history. It also demonstrates that Webb can take similar images of other distant exoplanets, opening the door to a wider survey of worlds orbiting far from their suns. Another target that has captured astronomers' imagination is the exoplanet WASP-39b. This world had already been observed by the Hubble Space Telescope and the Spitzer Space Telescope, but Webb's capabilities have allowed for a far more complete picture of its atmosphere. WASP-39b is a gas giant, slightly smaller than Jupiter, but with a very low density. So it is puffier and more diffuse. Conditions there are harsh, and life, as we understand it, is extremely unlikely. This planet orbits a G-class star named WASP-39, a star somewhat similar to our Sun but believed to be slightly smaller and cooler, likely due to its older age. WASP-39b itself is extraordinarily close to its star, circling at a distance of about 4 million miles, or around 7 million kilometers. That is about 8 times closer to its star than Mercury is to the Sunday. As a result, its atmosphere is heated to scorching temperatures, with average values around 1,600 degrees Fahrenheit. Previous observations had already hinted at the presence of water vapor, sodium, and potassium in the planet's atmosphere. Webb's instruments confirmed these findings and added new layers of detail. In its first year of operation, Webb detected sulfur dioxide, oxygen-bearing molecules, methane, and, for the first time on an exoplanet, a clear signal of carbon dioxide. The presence of sulfur dioxide is especially interesting because it arises from chemical reactions driven by starlight, a process known as photochemistry. On Earth, the ozone layer in our atmosphere forms through similar photochemical interactions, though the specific molecules involved are different. According to scientists such as Kazuma Ono at the University of California, Santa Cruz, the mix of gases observed on WASP-39b may even carry hints about the planet's past, suggesting that it might have migrated inward from a more distant orbit to its current, extremely close path. The detailed chemistry recorded there has not yet been seen on other exoplanets in such clarity. That makes WASP-39b a kind of laboratory in the sky, where astronomers can study how atmospheres form, evolve, and respond to intense radiation from their stars. In doing so, they move a little closer to understanding not only the climates of distant worlds, but also the long, intricate history of how planets themselves come into being. In the middle of all these fiery giants and distant, swollen worlds, Webb has also turned up something much quieter and more familiar in scale, yet just as stirring to imagine. In January of the year 2023, astronomers announced that the telescope had joined the long list of planet hunters, not just by refining what we know, but by actually discovering a new exoplanet of its own. While watching a small red dwarf star about 40 light-years away, Webb noticed a subtle, repeated dimming in the starlight. The pattern unfolded over just 2 transits, each one lasting a short orbit of roughly 4 days, as a small object passed in front of the star and blocked a tiny fraction of its glow. By measuring this dip with great precision, scientists could say with confidence that the object was a planet. They named it LHS-475b, making it the first exoplanet whose discovery is credited directly to Webb. This world is far too small and faint for Webb to photograph as a bright dot next to its star, at least for now. The telescope did not capture a picture of the planet in the way it can image some giant worlds far from their suns. Instead, it sensed the planet's presence through its effect on the star's light. Even so, researchers have already been able to sketch the planet's basic character. LHS-475b appears to be almost exactly the same size as Earth, not a gas giant or icy mini-Neptune, but a rocky world. It orbits much closer to its star than we do to the Sun, and its equilibrium temperature is estimated to be about 100 degrees Celsius higher than Earth's average, making it a rather hot, close-in planet. Whether LHS-475b has an atmosphere is still an open question. Webb's early measurements have not yet been able to confirm one, but they also have not ruled it out. A team led by Jacob Lustig-Jäger has suggested that if an atmosphere is present, it might resemble that of Venus, perhaps thick and heavy, made mostly of carbon dioxide, with clouds of reflective droplets. That is only a possibility, not a conclusion. Further observations will be needed to tease out the subtle fingerprints of gases in the thin band of starlight that passes through any atmosphere when the planet transits. Hidden in that light could be clues about composition, weather, and perhaps, very far down the road, even hints about weather conditions somewhere on such worlds could allow life. For now, Webb is still in the early stretch of its planned work. After reaching its observing point and unfolding into its full shape, it has only spent about a year truly looking outward. Together with the scientists on the ground, it has close to 9 more years of guaranteed operations ahead, and possibly more if its hardware and fuel last longer than expected. Its main goals are as broad as the cosmos itself: to study the earliest galaxies that formed after the Big Bang, to watch how stars are born and die, and to examine exoplanets and the planets of our own solar system in unprecedented detail. In the near future, Webb is expected to devote special attention to the intriguing system known as TRAPPIST-1, a compact family of small planets orbiting a cool red dwarf star. Several of those worlds lie in or near the star's habitable zone, where temperatures might allow liquid water to exist under the right conditions. Webb will be able to analyze the starlight that filters through any atmospheres they possess, searching for water vapor, carbon dioxide, and other molecules that shape climate and chemistry. Some of these planets, at least in principle, could be capable of hosting life, and even if they are barren, their atmospheres will teach us a great deal about how small, rocky worlds behave under different stars. Closer to home, Webb will turn its gaze toward the atmospheres of Mars, Pluto, Jupiter, and icy objects in the Kuiper Belt. By examining the composition and structure of these atmospheres and surfaces in infrared light, the telescope can help refine our understanding of how the solar system formed and evolved. Small differences in the abundance of water, carbon compounds, and other ingredients can reveal where each body was assembled and how far it may have migrated over time. Webb's sensitivity will allow it to pick up faint spectral lines that previous instruments could not clearly separate. Another important strand in Webb's future work is tracing the sources of water in planetary systems. To do that, the telescope will study places like Ganymede, the largest moon of Jupiter, which is believed to hide a deep internal ocean beneath its icy shell. By observing how light reflects and emits from its surface and exosphere, Webb can search for signs of water and related molecules, helping to map where ice resides and how it may move and cycle. Insights gained from Ganymede will also guide studies of other ocean-bearing moons, such as Enceladus and Europa, and possibly Mimas, all of which may harbor subsurface seas. Understanding these hidden oceans is not only interesting for planetary science, it also matters for astrobiology, because such environments could be potential habitats for life. Taken together, all these projects suggest that Webb's discoveries over the coming years may reshape our understanding of the universe in ways we can only partly anticipate. From the first galaxies to nearby icy moons, from hot, puffed-up gas giants to compact Earth-sized planets, it will continue to offer new pieces of a puzzle that stretches across space and time. But the universe is clever at surprising us, and it rarely lets us follow a single thread for long. As our attention drifts outward beyond the orbit of Mars, into the wide belt of rocks that circles the Sun between Mars and Jupiter, we find another kind of story waiting. Among the millions of asteroids that tumble silently through that region, one object stands out, not because it is flashy, but because it subtly refuses to fit into tidy categories. This is the dwarf planet Ceres, a small, round world that seems at first glance plain and gray. It floats almost unobtrusively in the asteroid belt, yet it has quietly unsettled our sense of cosmic order. Ceres was the first object ever to be classified as a dwarf planet, sharing this category with Pluto, and its existence has helped astronomers realize that the family of planets is broader and more nuanced than we once thought. Ceres also holds mysteries of its own. In the dark sea of dim rocks that surrounds it, this world shines with a slightly different character, marked by patches of unusual brightness on its surface. Bright spots that once puzzled observers and stirred speculation. Some of these luminous areas may be linked to salty deposits and perhaps to icy material beneath the crust. The possibility of cold, subsurface oceans and the chemistry they might host hint softly at the kind of environment where the raw ingredients of life could be stirred. This little world was first seen in the year 1801 by the astronomer Giuseppe Piazzi. At first, he thought he might have discovered a comet. Its faintness and small disk suggested something transient, but its motion across the sky was smooth and steady, more like that of a planet. At the time, some theorists, including Johann Lambert and others influenced by the Titius Bode pattern, had suggested that there ought to be a missing planet in the wide gap between Mars and Jupiter. Piazzi's find seemed to be a candidate for that long-suspected world. Illness eventually forced Piazzi to pause his observations, leaving the new object's orbit imperfectly known. Using the limited data he had recorded, the young mathematician Carl Friedrich Gauss developed methods to calculate the approximate path Ceres followed around the Sunday. His calculations were so skillful that other astronomers were able to recover the object in the sky, confirming that it was indeed circling in the region now known as the asteroid belt. Early estimates of its size were rough and often too small. Some observers believe Ceres to be only about 160 miles across, but later measurements revealed that its true diameter is closer to 584 miles. For a time, Piazzi and some of his contemporaries treated Ceres as a bona fide planet. Yet, as more and more small objects were discovered in the same region, the picture became muddier. Over the next centuries, Ceres was gradually reclassified by the wider scientific community as just another asteroid, albeit the largest one, making up about 1/4 of the total mass of the belt. It was not until the year 2006 that the International Astronomical Union formally recognized Ceres as a dwarf planet, alongside Pluto and a few others, restoring a measure of planetary dignity to this unassuming world. The importance of Ceres goes far beyond labels. By studying it up close, scientists have gained insight into how planets form. Ceres appears to be a kind of planetary embryo, an object that began to grow into a full planet but never quite finished the process. It shows us, in frozen form, a stage of development that larger worlds passed through long ago. In that sense, Ceres has helped expand our sense of what a planet can be, and it has prompted us to carve out a new category dwarf planet for bodies that are round under their own gravity but have not cleared their neighborhoods of other debris. Because Ceres is dim and far away, and because it lacks a dramatic ring system or large moons, it was long treated as a minor character in the solar system's story. Its mass is only a small fraction of Pluto's. Pluto is roughly 14 times more massive, and the gravitational influence of Jupiter likely kept Ceres from gathering enough material to grow larger. Surrounded by countless building blocks, it seems to have stalled, left at an embryonic stage without a clear chance to accrete much more mass. Ceres takes about 4 6/10 Earth years to complete one orbit around the Sunday. Its rotation, however, is swift. It spins once on its axis in roughly 9 hours, giving it one of the shortest days in the solar system. Its axis tilt is only about 4 degrees, nearly upright relative to its orbit, which means it experiences little in the way of seasonal change. There are no strong swings between winter and summer. Sunlight falls in a relatively steady pattern over the course of its long year. The nights on Ceres are deeply dark. The dwarf planet has no moons to reflect light and no rings to scatter sunlight in delicate arcs. It is simply too small to hold such structures in place. It orbits at about 3 times Earth's distance from the Sun, so the warmth it receives is faint. As a result, its average surface temperature hovers around -100 degrees Fahrenheit. Any heat that does reach the surface likely radiates away quickly. Ceres seems to lack a substantial atmosphere and has no significant magnetosphere to shield it from the charged particles of the solar wind. At first glance, it does not look like the sort of place where life would find an easy foothold. And yet, the surface of this little world hints at stories more complicated than simple lifelessness. Despite its age of roughly 4.5 billion years, Ceres does not bear the heavily scarred appearance one might expect. It has craters, but not as many as some other ancient bodies, and it lacks the truly giant impact basins that might suggest catastrophic collisions. One could imagine that an encounter with a large asteroid long ago shattered part of Ceres, erasing old marks and leaving a smoother face behind. But the real explanation, as scientists have begun to uncover, is different and no less surprising. When the Dawn spacecraft arrived at Ceres in the year 2015, it was like sending a small metal visitor to knock gently on the door of a long, quiet world. As it slipped into orbit and began its patient survey, Dawn mapped the dwarf planet's surface in careful detail. The picture that emerged was not the bare, dusty rock many had imagined, but something far more subtle. A crust made of a mixture of water, ice, and minerals, such as clays and carbonates. In many ways, Ceres resembles a rocky world, but because so much of it is ice and lighter material, its overall density is several times lower than Earth's. As scientists examined the smoothed rims of craters, the unusual bright patches at their centers, and the long furrowed patterns crossing the surface, a surprising conclusion took shape. Ceres is not a silent, fossilized relic. It is, or has recently been, geologically active. Something is refreshing its icy skin, erasing some of the scars of ancient impacts and painting new markings over old ones. The leading suspects are cryovolcanoes. Volcanoes not of molten rock, but of cold, salty water and slushy ice. Models suggest that Ceres may contain up to about 1/4 of its mass in water. Some of that water appears to have been able to rise toward the surface in the form of briny cryolava, seeping or erupting into deep craters and then freezing in place. Across the globe, Dawn's images reveal cliffs, canyon-like troughs, and networks of faults that hint at internal movement. There are also several dozen features that look like cryovolcanic domes or mountains, the tallest of which has been given the name Ahuna Mons. Ahuna Mons rises to a height of roughly 4 miles above the surrounding terrain. A solitary, bright-sided mountain that looks almost out of place on such a small world. What makes it even more intriguing is its age. Estimates suggest that Ahuna formed only about 1 billion years ago, which is relatively recent on the scale of the solar system. That means that until not so long ago, in cosmic terms, Ceres still retained enough internal heat to push icy material upward and build a mountain. A study, led by planetary scientist Maria Cristina de Sanctis, has gone further, suggesting that some cryovolcanic activity on Ceres may still be occurring, or may have persisted until comparatively recent times. Certain bright trails and deposits, which we will return to, look fresh enough to hint that the dwarf planet's interior has not gone completely cold. Such activity matters not only for reshaping the surface, but also for influencing whatever tenuous atmosphere Ceres can sustain. Unlike Earth, Ceres does not have strong gravity or a thick blanket of gas. It cannot hold a permanent, dense atmosphere. Instead, it has what scientists call a variable exosphere, a very thin, fleeting envelope of molecules that sometimes appears and then fades away. Eruptions, slow leaks of gas from the interior, and the gentle release of water vapor can briefly thicken this exosphere, allowing it to trap a bit more warmth. But this state is fragile. Solar activity plays a major role in whether Ceres has any discernible atmosphere at all. When sunlight falls strongly on regions rich in surface ice, the ice can sublimate directly into vapor, creating a temporary cloud of gas around the dwarf planet. Over the course of a few weeks, this sparse atmosphere disperses into space. Observations from instruments such as those at the European Southern Observatory's Very Large Telescope currently show no clear signs of a stable atmosphere around Ceres. It is as though the planet occasionally exhales, then falls quiet again. Among all its features, one particular crater has drawn special attention: Occator, a roughly 57-mile wide basin whose interior shines with some of the brightest patches on the dwarf planet. Occator is thought to have formed about 20 million years ago when Ceres was struck by a sizable object. The impact fractured the crust deeply, allowing subsurface water to rise toward the surface. As that water flowed and froze, it left behind long furrows and intricate patterns radiating outward from the crater. The impact did more than carve a scar. It acted like a hammer blow on a shell filled with brine. As water and slushy materials surged upward, they altered the surface minerals. Clays were washed and transformed into phyllosilicates, rich in magnesium and ammonium. Among the materials identified in these bright regions is a marine mineral called hydrohalite, previously known only from salty environments on Earth. Finding it on Ceres hints that similar processes of brine freezing and evaporating have taken place there. Taken together, these clues suggest that Ceres may once have been an ocean world. Beneath its crust of ice and rock, there could have been a deep global or regional ocean of liquid water. Today, that ocean is likely mostly frozen, but Dawn's data indicate that pockets and layers of liquid, salty water may still exist below the surface, especially beneath places like Occator. Estimates suggest that these brine reservoirs might lie at depths of around 25 miles. The crust above them, composed of ice mixed with gases such as methane and a variety of salts, acts as insulation, helping to keep the water from freezing completely solid. Maria Cristina de Sanctis has remarked that, by simple expectations, such an ocean should have frozen long ago. Ceres does not enjoy the tidal heating that keeps the interior of some icy moons warm. It does not orbit a massive planet as Enceladus or Europa do. It circles the sun directly, with no giant companion to flex its interior and generate heat. Yet Dawn's observations show that at least some liquid has persisted. The temperature in these briny pockets may be as low as -22 degrees Fahrenheit, but because the water is mixed with high concentrations of salts and minerals, it can remain liquid at those frigid values. Another researcher, Axel Heisinger and colleagues, have noted that without tidal pumping, Ceres must rely on heat left over from its formation and on radioactive decay within its interior to keep parts of its ocean from freezing. Over time, that heat diminishes, so the ocean cannot remain entirely liquid forever. In this view, the impact that created a crater played a crucial role. It cracked the crust, opened channels, and allowed the remaining brines to surge upward, driving episodes of cryovolcanism and leaving behind the bright marks that first revealed the presence of unusual materials on the surface. And so we return to those mysterious, luminous patches that gleam at the bottoms of Akator and other craters. These bright areas, some in a crater and some in craters with names like Cerealia and Venalia, reflect an astonishing fraction of the sunlight that strikes them, on the order of 50 to 60%. Their origin puzzled scientists from the moment dawn first sent back close-up images. At first, many researchers suspected they were simply freshwater ice deposits, or perhaps accumulations of frozen ammonia or methane frost. As the mission continued and spectrometers analyzed the light from these spots in more detail, another picture emerged. The leading theory now is that the brightness comes primarily from salts. When cryolava rich in dissolved salts erupts or seeps up from underground reservoirs and spreads across the cold surface, the water gradually evaporates or sublimates into space, leaving behind a crust of crystalline minerals. These deposits can include magnesium sulfate, similar to Epsom salt, and sodium carbonate, a kind of soda ash. In combination, they form highly reflective surfaces that glitter in sunlight against the darker background. Dawn's cameras and instruments have cataloged more than 300 such bright regions scattered across Ceres. They are not all the same. The most radiant patches lie on the floors of craters like Akator, where the material appears to be a mixture of salt-rich deposits and frozen water, perhaps replenished or reshaped over time. Other bright areas show up as streaks, rays, and delicate patterns extending outward from impact sites, the result of meteoroids striking the crust, excavating subsurface brines or salt layers, and splashing them across the landscape in thin, luminous veils. Over long stretches of time, the bright and dark materials on Ceres have not stayed neatly separated. According to researcher Nathan Stein, hundreds of millions of years of impacts, landslides, and slow surface motions have mixed them together to form much of the present crust. This suggests that billions of years ago, when the solar system was more crowded and collisions were more frequent, Ceres may have worn far more bright spots than we see today, perhaps well over 1,000 glittering marks scattered across its face. Why then are some of the existing spots so much brighter than others? The answer seems to lie in the details of how each one is made. In a place like Akator Crater, there is strong evidence for a subsurface reservoir of salty water. Cryovolcanic activity there may be more vigorous or more recent, continually bringing fresh brine closer to the surface. As this brine wells up and freezes, it leaves behind highly reflective salt deposits that renew the crater's brilliance. In another crater, often referred to as Cagliafula, the picture may be more intricate. Instead of a single, explosive event, cryolava might have ascended slowly through fractures in the crust, building a low dome beneath the surface. Inside that dome, the briny mixture could have churned and circulated, boiling in a slow, cold way for a very long time. Only after this extended simmer would the material have settled, freezing into a patchwork of ice and salt fragments that now lies exposed at the surface, a pale scar left by an ancient, hidden cauldron. What makes these processes especially intriguing is that they do not seem to belong entirely to the past. The formation of bright salt patches appears to be ongoing, if perhaps at a very gentle pace. Maria Cristina de Sanctis and her colleagues have identified evidence of sodium chloride ordinary table salt in regions like Akator. Under the conditions on Ceres, the water associated with such salts should have boiled away or sublimated into space within about 100 years of reaching the surface. The fact that the salt deposits still appear moist, still bearing the signature of water, implies that fresh material has been brought up relatively recently, at least in geological terms. These shining spots, then, are not just curiosities for the eye. They are signposts pointing to active or recently active geology, a living interior still capable of moving water and dissolved minerals around. And that, in turn, touches on one of the most profound questions we can ask about any world. Could it support life, even in its simplest forms? Ceres may be cold and exposed, but in many ways, it ticks important boxes for habitability, at least for microorganisms. Liquid water, even if briny and deeply buried, is the primary medium in which we know life can arise and endure. But water alone is not enough. To form even the most primitive cell, a world must offer a variety of chemical elements, especially carbon, which is wonderfully suited to building complex molecules. Data from the Dawn mission show that Ceres's surface contains abundant rocks rich in silicon and iron, but also an unexpectedly high amount of carbon. Roughly 20% of the surface mass appears to consist of carbon-bearing material, a proportion about 5 times greater than what is found in typical carbonaceous chondrite meteorites that fall on Earth. Moreover, much of this carbon is mixed with water and clay minerals. When such mixtures interact with oxygen and hydrogen, they can give rise to a wide array of organic compounds, simple sugars, alcohols, fatty substances, and other building blocks from which more intricate structures can be assembled. And carbon is not the only player. Water itself carries dissolved salts and volatile compounds, while the minerals within the dwarf planet have been transformed over billions of years. Inside Ceres, rocks similar to serpentine and various carbonates are thought to have been altered by heat from radioactive decay. As these materials warmed and reacted with water, they may have produced new minerals and released substances such as sodium, sulfur, and methane into subterranean brine pockets. Geophysicist Mohit Daswani has described these brines as a kind of chemical soup, a concentrated mixture of ingredients that could, in principle, provide a niche where life might gain a foothold. In the more tumultuous past of the solar system, when impacts were more frequent and powerful, Ceres would have received extra bursts of energy. Each large collision could have warmed the crust locally, stirred the interior, and perhaps opened new pathways for water to circulate. During those times, conditions in certain underground reservoirs might have been more favorable, at least briefly, for simple microbial life to begin or persist. Tiny organisms, if they ever arose, could have inhabited sheltered pockets of liquid water, protected beneath layers of ice and rock. Right now, though, our picture is incomplete. There are still major obstacles to declaring Ceres truly habitable. One challenge is the apparent lack of a long-lasting atmosphere thick enough to shield the surface from harmful radiation. Without such protection, any life at or near the surface would be exposed to harsh particles and ultraviolet light from the Sunday. A second uncertainty is the actual amount and distribution of liquid water today. We know that brines likely exist, but their volume, depth, and stability are not yet well constrained. Moreover, Dawn did not find clear evidence of large amounts of certain key nutrients, such as nitrogen and phosphorus, which are essential for the biochemistry of all known organisms. These elements could be present in small quantities or in forms that are difficult to detect from orbit, but until we sample the material directly, we cannot be sure whether Ceres has enough of them in accessible form to support even very simple life. To move beyond speculation, future missions will need to touch Ceres more intimately. Scientists are already thinking about the next steps. In plans discussed by NASA, astronomers hope that in a little more than 10 years' time, a new spacecraft could journey to Ceres with the specific goal of collecting samples from its surface and returning them to Earth. Researcher Julie Castillo-Raguez has pointed out that Ceres's proximity and low gravity make such a mission comparatively practical. It would not require the immense energy needed to land on and lift off from a larger world, and the return trip could be accomplished at a relatively modest cost. She and others are confident that the salts and surface materials of Ceres will contain organic matter preserved in ways that telescopes and orbiters can only hint at. Holding such samples in laboratories on Earth would allow scientists to measure isotopes, study complex molecules, and look for subtle signs of chemical pathways that might be associated with biological processes. Even if no living microbes are found, the presence of rich organic chemistry in frozen brines would shed light on how far prebiotic chemistry can progress in small, icy worlds. Ceres, in that sense, is an ideal natural laboratory. It offers a nearby test case for theories about how the solar system formed and how ingredients for life are assembled and stored in harsh conditions. By decoding its history, we can refine our models of planetary evolution, from the earliest stages of dust and ice aggregation through to the emergence of distinct classes of worlds: rocky planets, gas giants, icy moons, and dwarf planets that straddle the boundaries. Future research on Ceres may turn out to be a quiet turning point in cosmology. If we find that this small, overlooked world hosts, or once hosted, even the simplest forms of life, it would show that biology can take root in places far more modest than Earth. It could hint that icy oceanic worlds scattered around other stars and hidden beneath the shells of distant moons deserve even more attention than they already receive. And even if Ceres turns out to be lifeless, its lessons will still be profound. Understanding how water, rock, and organics interact in its depths will help us read the stories written in many other bodies across the galaxy. In its dim orbit between Mars and Jupiter, this inconspicuous dwarf planet may quietly guide us toward dozens of similar worlds, each with its own buried ocean, its own slow chemistry, and its own secrets waiting in the dark.